Hey there, future engineers. Welcome to AB Engineering Guild, your go-to channel where we simplify the science behind real-world engineering. In today's video, we're diving into open channel flow formulas, the essential tools that help us understand how water behaves in irrigation canals, rivers, drainage systems, and more. From calculating velocity and discharge, to using Manning's and Shays equations, we've got it all laid out in a way that's easy to follow, even if you're just starting out. So, grab your notebook, hit that like button, and let's break it down. Let's explore the importance and applications first, then we'll get into the formulas themselves. 1. Accurate channel design and sizing. First off, open channel formulas help us design and size channels accurately. That means we can calculate the right width, depth, and slope that a channel needs to carry a certain amount of water safely. For example, if you're building an irrigation canal for a rice field, you need to make sure it can deliver enough water without overflowing during peak use. If the channel is too small, it will flood. If it's too big, you waste materials and money. So, the right dimensions are everything, and that's where these formulas come in. 2. Prediction of flow behavior. Next, formulas let us predict how water will behave under different conditions. Let's say the slope changes along the canal, or there's roughness from grass or stones lining the bottom. These factors affect flow speed and depth. Using equations like Manning's or Shays, we can simulate these changes before anything is even built. For instance, if we know a drainage ditch will cross different soil types, we can adjust our design to keep the flow smooth and controlled all the way through. 3. Optimization of efficiency and cost reduction. Another huge benefit is cost efficiency. When we calculate flow precisely, we avoid over-designing, which means we don't overspend on concrete, land, or labor. And we also avoid under-designing, which can lead to system failure and costly repairs later on. Think about flood control systems. A poorly designed channel could mean millions in damage after just one heavy rain. So, every correct calculation translates to money saved and disasters prevented. 4. Safe water conveyance and hazard prevention. Lastly, correct application of these formulas ensures safe water conveyance, meaning water moves exactly where we want it, without causing damage. This is especially important in places prone to erosion, like hilly areas or riverbanks. A well-designed open channel will reduce water velocity in sensitive spots and prevent scouring or sediment buildup. That protects farms, roads, buildings, and even entire communities from the risks of flooding and land degradation. So, as you can see, learning open channel formulas isn't just about math, it's about making smarter, safer, and more sustainable engineering decisions. Now that we know why open channel formulas are important, let's take a look at how they are applied in real-world situations. 1. Agriculture, irrigation canals for crop production. First, in agriculture, open channels are used to design irrigation canals. These canals distribute water efficiently across large farm fields, ensuring that crops get the right amount of water they need for healthy growth. Without proper channel design, irrigation systems can waste water or fail to deliver enough to the plants. 2. Urban drainage, stormwater management systems. Second, in urban areas, open channels are critical for stormwater management. During heavy rains, these systems quickly carry away excess rainwater to prevent flooding in streets, homes, and businesses. Well-designed urban drainage channels keep cities safe and functional even during extreme weather. 3. Flood control, river engineering and levee design. Third, open channels play a major role in flood control. Engineers design and modify river channels, build levees, and create diversion systems to control river flows during flood events. This protects farmlands, towns, and even major cities from devastating flood damage. 4. Energy, hydropower channels and cooling water systems. And finally, in the field of energy, open channels are used in hydropower plants to direct water flow toward turbines. They are also important in cooling water systems for power stations, where large volumes of water are needed to regulate temperatures. Without carefully designed channels, these critical energy systems wouldn't function properly. As you can see, open channel design is everywhere, from farms and cities to rivers and power plants. Mastering these applications is key for agricultural and biosystems engineers like us to make a real difference in the world. Next, fundamental hydraulic formulas for open channel flow. Let's start with one of the most basic and essential formulas in open channel hydraulics, the velocity flow rate equation. This formula tells us how fast water is moving through a channel. It's simple and straightforward. Velocity equals the flow rate divided by the cross-sectional area of the channel, where V is the flow velocity in meters per second, Q is the flow rate or discharge in cubic meters per second, and A is the cross-sectional area of flow in square meters. This equation is especially useful in real-world applications like checking the speed of water in irrigation ditches, laboratory flumes, or stormwater drainage canals. If the velocity is too high, it might cause erosion. If it's too low, water might not move efficiently. So, this equation helps engineers find that sweet spot. Next up is the discharge formula, one of the most important ones in open channel hydraulics. It tells us how much water is passing through a channel per second. To find that, you just multiply the velocity of the flow by the area of the channel. Discharge equals area times velocity. This is widely used in designing the capacity of irrigation canals, culverts, and stormwater drains. Manning's velocity equation, metric system. Now, let's talk about Manning's equation, a favorite among engineers. This helps us estimate the velocity of water flowing through a channel based on how rough the surface is, the shape of the channel, and how steep it is. Velocity equals 1 divided by the Manning's roughness coefficient, multiplied by the hydraulic radius raised to the 2/3 power, and then multiplied by the square root of the slope. It's commonly used when you're designing concrete or earthen canals and want to know how fast the water will flow depending on the materials and slope. Manning's velocity equation, English system. His one is just like the last, but used in countries like the US that use feet instead of meters. The only difference is that instead of 1 in the formula, you use 1.486 or sometimes, as rounded up into 2 decimal places, we use 1.49 as a multiplier. Everything else, roughness, hydraulic radius, and slope, stays the same. It's just tailored to imperial units. Shay's equation is another way to calculate velocity in open channels. It's a bit simpler and older than Manning's, but still useful. Its formula is velocity equals the Shay coefficient multiplied by the square root of the hydraulic radius times the slope. Instead of using a roughness coefficient like in Manning's, this formula uses the Shay coefficient, a number that combines the effects of roughness and flow conditions. In here, we can see that Shay's coefficient varies based on the system's use. In metric system, hydraulic radius in metric, we use 1 as a multiplier. But in English system, where hydraulic radius is in feet, we use 1.486 or 1.49. Slope of the channel, the energy line gradient. Formula. We have the slope formula, which measures the steepness of the channel. S equals delta H divided by L, where S is the slope, delta H is the change in elevation or height of the water surface, and L is the length over which that change occurs. A steeper slope means faster flow, while a flatter slope results in slower movement of water. Lastly, we have freeboard. This is the vertical distance between the surface of the water and the top edge of the channel. Think of it as your safety buffer, to prevent water from spilling over during high flows. There are a few ways to calculate freeboard, depending on how deep the water is. If the water is between 0.3 to 2 meters deep, the freeboard should be 0.4 times the depth of the flow. If the depth is more than 2 meters, then the freeboard should be 0.25 times the depth plus 0.3 meters. And if you're accounting for high-velocity flows, then the freeboard is calculated as 0.5 times the flow depth plus the velocity head, and then add an extra 5 to 15 millimeters just to be safe. This is used in the final design step to make sure the channel won't overflow during extreme conditions. Now let's talk about the design of non-erodible open channels, which are commonly built using strong, durable materials like concrete. These types of channels are designed to resist erosion or scouring, even under high flow conditions. Material forming the channel, concrete. For non-erodible channels, concrete is the most commonly used material. It's strong, durable, and easy to form into the desired shape. When designing with concrete, we need to consider its Manning's roughness coefficient, or simply the N value, which represents how much resistance the channel surface creates to flowing water. The minimum value of N is 0.012. The maximum value is 0.018. For standard design purposes, we use N equals 0.015. This roughness value will be plugged into Manning's equation later on to calculate flow velocity. Minimum permissible velocity. Because concrete is non-erodible, there's no maximum velocity limit. It can handle fast-moving water without getting damaged. However, we must still avoid silting, or the buildup of sediment, especially if water moves too slowly. That's why we follow these minimum velocity guidelines. Minimum velocity, between 2 to 3 feet per second. In metric, that's about 0.6 to 0.9 meters per second. For practical design, we often use 2.5 feet per second, or 0.76 meters per second. This ensures that water keeps moving fast enough to carry sediment along and keep the channel clean. Channel bottom slope. Next, we consider the slope of the channel bottom, which is largely determined by the natural topography of the land. In irrigation projects, the slope must be designed to ensure that water downstream reaches a level high enough to divert into fields, without needing pumps. So, the slope needs to be just right, not too steep, not too flat. Channel side slope. Now for the side slopes of the channel, these depend on the soil or material used to form the channel bed and walls. Engineers use standardized slope ratios for different materials to prevent collapse or slippage. Here's a table showing the different materials and its indicated side slope, depending if it is a shallow or deep channel. These values are usually selected from a reference table based on stability and safety. Freeboard in open channel design. Finally, let's not forget about freeboard, often abbreviated as FB. Freeboard is the vertical distance between the surface of flowing water and the top edge of the channel. It acts as a safety margin, a buffer zone that helps prevent overflow in case of sudden surges in water level, waves, or unexpected heavy flow. Now, there are several guidelines and methods to determine the right amount of freeboard in open channel design. Let's go through them one by one. 1. Percentage method. Rule of thumb. One simple rule is to set the freeboard as a percentage of the flow depth, y. Freeboard equals 5% to 30% of the design depth. So in formula, FB equals 0.05y to 0.30y. In practice, we usually aim for a combined depth plus freeboard, meaning y plus FB, to reach a practical round number like 1.0 or 1.5 meters, depending on the project. 2. USBR method. U.S. Bureau of Reclamation. This is a standardized approach especially for irrigation and large canals. For small laterals with shallow depth, FB equals 1 foot, or 0.3 meters. For large canals with flow greater than 3,000 cubic feet per second, or 85 cubic meters per second, FB equals 4 feet, or 1.2 meters. This method gives a fixed safety height based on flow classification. 3. Ordinary condition formula. Under normal conditions, another formula is used based on flow and depth. Abacus freeboard equals the square root of the product of C and Y. In formula form, FB equals square root of C times Y, or FB equals square root C times Y, where C is a constant that depends on the flow rate. UC equals 1.5 if the flow rate Q less than or equal to 20 cubic feet per second, or 0.57 cubic meters per second. UC equals 2.5 if the flow rate Q greater than or equal to 3,000 cubic feet per second, or 85 cubic meters per second. Y is the flow depth in feet. This method adjusts the freeboard based on how much water is flowing, giving flexibility for different situations. Why freeboard matters. Setting the right freeboard prevents serious issues like water overtopping the banks, damage to adjacent farmland or roads, collapse of channel walls due to wave action. So, whether you're designing a small irrigation ditch or a large flood control canal, calculating freeboard is a must to ensure safety and reliability. In open channel flow, the shape of the channel plays a crucial role in how water moves. Each channel shape has unique advantages and is chosen based on the type of flow, stability needs, and construction requirements. Let's explore the most common shapes used in open channel design and understand why selecting the right one matters. Understanding different shapes of open channels. Now let's talk about something that plays a big role in how water moves, the shape of the channel. Different channel shapes are used for different purposes, depending on the type of flow, cost, stability, and where the channel is being built. In this part, we're breaking down the 5 most common open channel shapes and where each one works best. 1. Rectangular channel, simple and efficient for basic drainage. Rectangular channels are probably the easiest to understand. They have a flat bottom and vertical sides, making them simple to design, build, and calculate. They're commonly used in laboratory flumes, urban drains, and irrigation ditches, especially when flow conditions are controlled and consistent. They're ideal when you want straightforward construction, and land space or materials are not a major issue. 2. Trapezoidal channel, best for stable natural flows. Next, we have trapezoidal channels, which are widely used in real-world applications like irrigation canals, river training works, and drainage ditches. Their sloped sides help prevent erosion, and they can carry more flow efficiently. Because of their shape, they blend well with the environment and offer better structural stability, especially in earthen or unlined channels. 3. Triangular channel, best for small, temporary, or roadside flows. Triangular channels are often used when flow is minimal or temporary, such as roadside ditches, storm runoff drains, or small-scale agricultural trenches. They're easy and cheap to construct, especially in natural or undeveloped areas, but they're not as efficient for larger, long-term flows. Still, for simple tasks like moving rainwater away from roads, they're a great choice. 4. Circular channel, perfect for pipes and underground flow. Circular sections are mostly found in closed conduit systems, like sewer lines, culverts, and stormwater pipes. They're designed to handle pressure and variable flow levels. Even when they're only partially full, their shape allows water to flow efficiently. Plus, their curved design resists soil pressure very well, which makes them excellent for underground applications. 5. Parabolic channel, great for smooth, gradual flows. Parabolic channels are less common but have some unique advantages. They're shaped like a gentle curve, like a bowl, and are used where smooth flow transition is important, such as in highway drainage, environmental canals, and naturalized designs. Their curved sides reduce turbulence, slow down flow, and help prevent erosion, especially useful in areas where the appearance and environmental integration also matter. When it comes to rectangular channels, the math behind them is refreshingly straightforward. Since the sides are vertical and the bottom is flat, calculating things like area, wetted perimeter, and hydraulic radius becomes very simple, and that's why this shape is so popular in controlled environments like lab flumes and irrigation ditches. There are 2 key formula sets you should know. 1. Custom cross-section design. This set of formulas is used when you're working with any general rectangular section. It includes how to calculate the flow area, the wetted perimeter, bottom width, and the hydraulic radius, which are all critical when determining how fast and how much water the channel can carry. These formulas are essential during the initial design phase, where you adjust dimensions to meet the specific needs of a project. 2. Best hydraulic cross-section, or most efficient section. Now, if you're aiming for the most efficient flow, there's a special version of the formula that gives you the best hydraulic cross-section for a rectangular shape. This version is optimized so that the water flows with the least resistance and the highest efficiency, making it ideal for saving materials and reducing energy losses. Trapezoidal channels are some of the most commonly used in real-world projects because of their stable sloped sides. When designing a trapezoidal channel, we use a full set of formulas that include area, wetted perimeter, hydraulic radius, top width, bottom width, and depth. There are 2 main categories of formulas for this shape. The custom cross-section formulas let you tailor the channel design based on the specific width, depth, and side slopes you want to use. On the other hand, the best hydraulic cross-section formulas help you find the most efficient proportions to maximize flow and minimize resistance, making it ideal for long-term performance and material savings. Formulas for triangular channels. Triangular channels are simple and often used in places like roadside ditches or temporary flow paths. The formulas used in triangular designs also cover the area, perimeter, hydraulic radius, and depth, but because of the V-shape, they rely more heavily on the side slope angle. For triangular channels, the custom design formulas allow flexibility depending on the slope you want to use. And for more efficient flow, there's the best hydraulic cross-section, which gives you the ideal shape that balances flow capacity with reduced resistance. Formulas for circular channels. Circular channels are widely used in sewer systems and stormwater drains because of their structural strength and ability to handle varying flow rates. Their formulas are a bit more involved since the flow area and perimeter change with the depth of flow. But they still cover all the essentials like flow area, perimeter, hydraulic radius, and depth, just shaped around a circle. The custom formulas are used when flow is partial or varies throughout the day. The most efficient cross-section for circular channels tells us at what depth the flow is maximized for a given diameter, ensuring high performance even during peak loads. Formulas for parabolic channels. Parabolic channels are often used in naturalized drainage systems or highway runoff channels because they offer a smooth transition for water flow. The formulas for these channels help calculate the area, perimeter, hydraulic radius, depth, and top width, but they're shaped according to a curved parabola. With custom formulas, you can design the curve and depth to match the flow you need. The best hydraulic section gives you the ideal parabolic profile for efficient water movement, especially in applications where aesthetics and flow control are both important. Quick recap. Rectangular, great for basic and controlled flows. Trapezoidal, the most versatile and stable. Triangular, simple and effective for small or temporary flows. Circular, efficient for underground and closed systems. Parabolic, smooth and natural for special design conditions. And that wraps up our dive into the different shapes and essential formulas in open channel flow. From rectangular to parabolic channels, each shape has its own purpose, formulas, and ideal applications. Knowing how to apply the right design and equation can make all the difference in ensuring efficiency, safety, and sustainability in your water conveyance projects. If you found this helpful, don't forget to like, share, and subscribe to AB Engineering Guild for more simplified engineering content made just for you. Got questions or video suggestions? Drop them in the comments, we'd love to hear from you. Until next time, keep designing smart, and keep engineering with purpose. See you in the next video.